Good morning, everybody. I am Dr. TMP Rajkumar and teaching fiber optics and networks. Today, I am starting with a new chapter that is fiber optic couplers and connectors. This is a very small topic, but it is very important. And here, the two books to be referred is that is a optical fiber communication written by Gerd Kaiser, 5th edition, McGraw-Hill publication. The second book to be referred, that is Optical Fiber Communication by John M. Senior, Pearson Education, and it was reprinted in 2007. Fiber couplers and connectors. This is one of the very important stream of optical communication. And here, let me start with the introduction part. After completion, let me go through the fiber alignment and joint losses. Thereafter, single mode fiber joints. Then, fiber splices, fiber connectors, and fiber couplers. Introduction. Fiber optic communication, there are so many advantages, and I have mentioned these things in the first chapter. It has wider, larger bandwidth, less losses, security is very high, and at the same time there are many applications on optical fiber communication. But every system it has unique advantages and specific drawbacks. And like that, there are certain disadvantages. There are many losses. Even though it is a sophisticated technology, certain losses are there. In the previous chapter, I discussed this one. That is, it has absorption losses, bending losses, and losses due to waveguide dispersion, material dispersion, and many other core cloud interfacing, etc. There are so many losses. Apart from this, there is one more loss that I am going to cover now. That is fiber related losses. This may be temporary losses also. Sometimes it is permanent also. Now, let me start with this one. In any fiber optic communication system, in order to increase the fiber length, there is need to join the fiber length of fiber. That means in practice, in practical system, many fibers which are joined together to form a single structure. Because in the practical application, the distance of communication may be so many kilometers, maybe 100 kilometers or 200 kilometers, and it is faster communication which provides larger bandwidth, but one fiber cannot be drawn from sending point to destination point. There are so many fibers which are joined together very sophisticated way, and it makes a single structure. It has practical reality also. Length of communication that must be increased. That is one of the criteria. At the same time, there should not be any losses when you're joining two fibers. And here, the interconnection of fiber causes some loss of optical power. If we lose some power, and we are losing information also. Loss of power that must be minimized, that must be reduced. At the same time, we have to connect so many fibers together. Practically, there is a fiber of 500 meters length, and all 500-meter length fiber that are joined together form a single structure. It is a difficult task, but practically that is feasible. Here, the different techniques are used to interconnect fibers. Here, because the reason is that the core is a very smallest particle. That is in terms of microns, and core is the innermost particle of the fiber. Cladding is the next concentric cylinder. There is a total internal reflection occurs. Due to total internal reflection, and light signals move from one end of the fiber to another end of the fiber. And to join this core to core, cladding to cladding, the interfacing between core to core and cladding to cladding, that is very important. It is not that much easy. That is known as connectorization of two fibers. And when you are joining two fibers, certain microscopic machines are used. A connectorization should be proper. Then only the power will be coupled from one fiber to another fiber. Here, there are two varieties. A permanent joint of cable is referred as a splice. That is, it is a permanent structure, and fibers once it is laid down means splice connections are made, and it is giving connectivity from one place to another place, one town to another place. That is the splice connections. And second one, and a temporary joint can be done with the connector. So here connectors means we can dismantle it, we can reconnect it, and this is a temporary structure. A splice is a permanent connection, and this one is a temporary connection. Now let me go through one basic equation. In the fiber alignment, it must be proper. There should not be any gap between one fiber and to another fiber, and it must be reduced. Otherwise, it must be completely the space between one fiber and to another fiber end. There should not be any gap. There should not be any leakage of power. There is a formula that is NF, the coupling, N for the coupling efficiency or coupling power, that is equal to M common by ME. Here, the fraction of energy coupled from one fiber to another fiber proportional to common mode volume, that is M common. That means there are so many modes which are responsible for power propagation, especially in multimode fiber. And here M common, that is a common mode volume, common mode, and many modes are responsible for the light propagation. And the fiber to fiber coupling efficiency given in the above equation, the equation which I said, NF is equal to M common by ME, where ME is the number of modes in fiber which launches power into the next fiber. ME is very important. Number of modes are very important, and there is a dominant mode, and other modes also. Dominant mode responsible for highest power propagation, and other modes also supportive. The fiber to fiber coupling, that is known as fiber to coupling loss. Let me say loss, coupling loss, that is LF, which is given like this. That is LF is equal to minus 10 log of NF. N is coupling efficiency, and minus, that is indicating that there is a loss here. When there is a splice connection or connector, if you are connecting two fibers, joining two fibers, there is a loss, a small amount of loss takes place. That loss is mentioned in terms of LF. That is LF is equal to minus 10, and here power we are measuring, that's what 10 is taken, log of coupling efficiency of that. Now, practically what is happening, there is a misalignment between two fibers. The misalignment, that is because of improper connectorization. This is also said to be mechanical misalignment. Here, the diameter of the fiber, that is a few micrometer, and one cannot connect manually. We cannot connect one fiber to another fiber. A core diameter, that is a maximum of 100 micrometer, and cladding is maximum of 400 micrometer. Such a small one, it manually difficult to connect. This is one of the biggest problem that leads to losses. Hence, a microscopic alignment is very much important, and it is required. If the radiation cone of emitting fiber does not match the acceptance cone of the receiving fiber, then radiation loss takes place. Here, radiation loss is nothing but light losses. So, some amount of light we are losing, that is due to improper connection, that may be due to misalignment, that may be due to disalignment. A fiber to fiber connectorization should be proper. So if you are not succeeding in that, some amount of power will be losing. We are losing that one, and that causes minimization of the distance. The distance of communication enormously reduced. The magnitude of radiation loss depends on the degree of misalignment. Here, the main prime importance in the optical communication, that is the distance of communication. With the available power which is transmitted that should reach the destination. Due to many splice connections and temporary connections that is might be LED, that is a transmitter to fiber or fiber to detector. There may be many repeaters in between. So these things causes huge amount of losses. And also splice connections. Of course, splice is a permanent connection. The loss due to a single splice is very less, but it is a cumulative. It is added. There are so many splice connections from sending point to receiving point. So this we have to consider. Total loss due to splice connection, that is also enormous, and that is shown here. There are so many mechanical misalignments which causes losses, which uh, which is not coupling power from one end of the fiber to another end of the fiber. The one of the first this one, that is a lateral or axial misalignment. This is one of the mechanical misalignment. You can see the diagram here. In this diagram, the one end of the fiber that is not exactly connected to another end of the fiber. The core is not properly interfacing with the other part of the fiber. There are two fibers we are connecting. The core to core interfacing is very much essential. Similarly, cladding to cladding interface. So this is a small mechanical misalignment. This causes heavy losses. A loss of optical power means loss of information. We can say that the information and light power, both we can interrelate. The second type is longitudinal misalignment. The longitudinal misalignment, that is shown in the second diagram, and here there is a small separation between first fiber to second fiber. We want to join together, but there is a small, it may be in terms of microns. And the difference that is shown here, that is the S indicates separation between two fibers. So this must be minimized or we have to make it zero. But practically it is difficult to make it zero. We have to minimize that one. How to minimize? Minimize that can be minimized by taking proper care. Proper splicing can be done. Proper connectorization that can be done. In the first case, the lateral or axial misalignment, the D should be, the D is nothing but that is the separation, that is a nothing but that the lateral separation that must be minimized, and core to core interfacing and cladding to cladding interfacing must be proper. We can make it proper, and D must be reduced. But in the second one, S must be reduced. Let us go to the third one. Third one is the angular misalignment. This is also very much common in practice, and when fibers are joined together, there is some difference in angle. We are expecting the core to core interfacing and cladding to cladding interfacing, but especially in multimode fibers, this angular misalignment is very much common. That is denoted by theta, that is clearly shown here. And theta, as theta is more, theta may be 1 degree or part of 1 degree, but that causes huge losses. When you are joining two fibers together, this misalignment, and it is accumulative. There are so many splice connections. It is accumulated, and it causes maximum loss for a particular distance. The amount of power which is to be reached to the destination that may not reach, the distance of communication comes down. That is a major problem of this misalignment. Now, some more information about lateral misalignment. In the lateral misalignment, it's a lateral or axial misalignment occurs when the axes of two fibers are separated by a distance d. This I said already. The d must be minimized. Similarly, longitudinal misalignment occurs when fibers have same axis but their end faces are separated by a distance s, and this may be manufacturing defect. Sometimes we have to cleave the fibers properly. The end face fiber, it must be properly dressed, clear, and thereafter we have to join these two together. A proper splicing should be done, but in spite of that, there are small amount of losses which causes, that is due to separation of two fibers. Now, if you see one more very angular misalignment, and here this occurs when fiber axis and fiber end faces are no longer parallel. It must be parallel. If it is parallel, definitely there is no loss of power, loss of optical power. There is an angle theta between fiber end faces that is shown in the diagram. The axial or lateral misalignment is most common in practice, which causing considerable power loss. Compared to longitudinal misalignment and axial misalignment, the loss due to angular misalignment, that is maximum, it is more pronounced. This must be reduced. So this is happening because improper splice connection or improper connectivity, etc. The axial offset reduces the common core area of two fibers end faces, which is shown in the diagram. You can see another diagram I'm showing, and here there is a too much difference. We can understand this one very clearly. There are two circles are here. There is an axial offset of fibers, and A is the radius of the fiber, and two fiber, that is the emitting area and receiving area. Receiving fiber and emitting fiber both should be aligned properly, but it is not clearly aligned. There is a hatchet portion only it is aligned. That means core to core interfacing is not properly aligned, and cladding to cladding interfacing also not aligned. It is completely, it is departed. You can understand very clearly. And D is the separation. And here D must be minimized here. And one more very important thing is that, and it is the emitting area and receiving area, both are common, both are same circles. Radius of these two fiber end faces both are same. By proper connectivity, proper splicing, the angular misalignment can be reduced. Now, we can express this one mathematically. There's the angular misalignment. There's a A common. A common is very important, which is responsible for the power transfer. That is expressed in terms of 2A square across D by 2A minus D into A square minus D square by A to the square of 1 by 2. That is a square root of that one. That means the optical power coupled is proportional to common area of the two fiber cores. The common area which is given by this expression, and here A is the core radius of the fiber and D is the separation of the core axis. And here the main important thing is that D is the separation of the core axis that must be changed here, that we have to alter that one, and that is clearly mentioned in the equation mathematical expression. A common depends upon A common depends upon D also, and this can be done with proper care, proper alignment, and we have to avoid misalignment. Then definitely the maximum amount of power from one fiber to another fiber, it will be coupled. Next, let us go through some more expression for this. And here, the coupling efficiency. Here, the coupling. Let me say coupling. What is coupling? And power from one fiber to another fiber, it must be properly coupled. Coupling efficiency, it must be 100%. Practically, it is not feasible. Coupling efficiency for a step index fiber, if we consider step index fiber, it is the ratio of the common core area to the end face area. That is for this coupling efficiency for the step index fiber, that is equal to A common by pi A square, and here pi, that is a term which is taken, mathematical term, and A is the radius of the core, and this is given, that is once again it can be expressed like this: 2 by pi across D by 2A minus D by pi A into 1 minus D by 2A square again under square. This is for the angular misalignment. The angular misalignment, that is more common, that is in practice compared to other two misalignments. Now, let me go through some more information about angular misalignment, and here this is nothing but PT. PT, that is a total power, that is expressed like this. This is for the graded index fiber. Let me differentiate graded index fiber and step index fiber. Step index fiber, that was first it was coming to the picture, and it provides lesser bandwidth. But graded index fiber, especially designed, specially fabricated, and this provides maximum bandwidth. So data rate is maximum with the graded index fiber. At present in telecommunication, we are using graded index fiber. So we are highlighting graded index fiber but the graded index fiber, that is derived from the step index fiber. Now let me give a mathematical expression for the graded index fiber. The total power which is transferred from one end of the fiber to another end of the fiber, that is 2 by pi into P across D by 2A minus 1 minus D by 2A square under square, and again D by 6A into 5 minus D square by 2A square, and this is the expression. And there is a, we can minimize this one, that is for graded index fiber, the total received power for axial misalignment is given in this particular expression. That is the total received power for axial misalignment, and where here P is the power in emitting fiber, and this is when D is less than A. D is less than A. You know what is D? A is the radius of that one, and D is the separation of that one. And above expression, which is shown in the second equation. Second equation, that is if D is very less compared to A, then the above expression can be simplified like this. It's a very simple, and we have to go for second equation. We have to make D must be very less than A, and it must be like 100 times less than A, or 75 times or 80 times less than A. Then angular misalignment can be reduced. With this, I'll complete this misalignment and fiber coupling losses, etc. Next class, let me continue with the another one.